Okay, the very first thing I would like to do, if we have time, is to go through our flashcards. We learn everything through repetition, and so if the more often we can do this, the better as far as memorizing these flashcards. All right, so here is the first one. I want to know, Fernanda, what is the derivative of secant of x? Isn't this one secant of x times tangent of x? Remember secant of x times tangent of x? I don't know if that rings a bell. Sam, what about this one? What is the derivative of cosine? Isn't it negative sine of x? Question?
What was the first line?
Okay, let's go all the way back. Aren't these ones on canvas? Didn't I put all these on canvas? So it should be if you wanted to have access to all of these, if you go to modules and then you scroll to the top. And then flashcards right here. So that would be another way of seeing all of our flashcards. Okay. All right, so the derivative of secant of x. These are things we have to have memorized cold. The derivative of secant of x is? Yeah, secant of x times tangent of x. The derivative of cosine of x is? Negative sine of x. We need to have these memorized. The derivative, I'm sorry, this is the limit. The limit as x approaches infinity of sine of x over x, it is 0. Am I going too fast? Go back. Okay, so cotangent of x is negative cosecant squared of x, correct. Am I going too fast? All right, the derivative of cosecant of x.
Negative cosecant of x times cotangent of x.
Yeah, negative cosecant of x times cotangent of x. You asked? The limit as x approaches infinity of cosine of x over x. It is 0. The limit as x approaches 0 of sine of x over x. 1. What is the derivative of sine of x? Cosine of x. What is the derivative of tangent of x? Secant squared of x. Secant squared of x. Okay. Today we are going to be adding 6 more cards. So hopefully we are learning these as we go through. If we wait for the last minute to try to learn all of these, it's just going to be too much information. So let's make sure we are learning as we are going on this. So the assignment that is due today is 4.4. And 4.4 is on the derivatives of inverse trig functions. All right, so if I had something like y equals sine of x, this is a periodic function and it is going to oscillate back and forth between -1 and 1. It'll start at the origin here and then just start oscillating back and forth. Not sure if I like how well I drew that. Something like that. How long is a period for sine of x? What's the period? Yeah, it's 2 pi. So that means we are going to, if you start at, I don't know, springtime, and then you advance into summertime, and then fall, and then winter, and then springtime again, we are looking at 2 pi. That is 2 pi. Now let's look at the inverse of this. Now the inverse is a reflection across the y equals x. And it's interesting also that with an inverse that the x's become the y's and the y's become the x. So I'm going to just draw a line here. This is my y equals x. And then I'm just going to reflect everything across that. Now again, our x's become our y's and our y's become our x's. So I'm going to get something, the range from -1 to 1 is now going to become my my domain from -1 to 1. Now let's consider too what happens when, let's look at our unit circle. And let's see what happens when we go from, is that my x or my y value? It's my y value. So when I go from -1 to 1, so this would be 1, and this is my 1, my -1 here. We're looking at this little piece right here. So we're just going to reflect that one little piece, something like this, something like that. And when our x's become our y's and our y's become x's, we just found that, that range from -1 to 1 becomes my domain. Well, what's from here to here, what are my angles? From what to what? What are my angles from here to here? What's this rotation here? We always start at the initial side. Yeah, it's going to be -π². So that becomes -π². And then when we rotate here from our initial side, we get π². That becomes my π². Now the question is, why am I stopping there? Why don't I just continue on with my graph forever? My inverse. Why am I stopping just at this little green part here? It's not going to be a function anymore. Yep. So when our x's become our y's and our y's become our x's, if the range is from -1 to 1, if the range of my original function is from -1 to 1, then that range becomes the domain from -1 to 1 of our function. So that would be another explanation of why we're just looking at this one little piece here. One more time. If the range is from -1 to 1, and part of an inverse, the relationship of an inverse, the relationship between the function and the inverse is that your x's become your y's and your y's become your x's, then we're limited with our new, if our range was from -1 to 1, that becomes the domain, and we're limited as well with the domain from -1 to 1. So we just have that one little piece, that little green piece right there. And that little green piece would be the equation. Let me just go backward and get rid of some of this mess here. That green piece is the equation y equals what? This green piece right here. The equation is y equals what? Yeah, the inverse of sine of x. It becomes the inverse of sine of x. Now, what about, so the inverse of sine of x, this is a calculus class where derivatives are really important. In fact, everything sort of centers on this idea of the derivative. When I look at the graph, where this graph here, is the graph, the green graph, differentiable at all values of x? Is it differentiable from -1 to 1? So what this with the red graph, if you follow the red graph, what is this point right here, or what's the derivative of this point right here on the red graph? What's the slope, the instantaneous rate of change for the red graph? Yeah, it's a 0. Yeah, my tangent line would be like this, right? It would be 0. What is that point on the green graph? The slope would be what? What's the slope on the green graph? If the red graph gives us a horizontal tangent line, doesn't the green graph give us a vertical tangent? Is a vertical tangent differentiable? There are 4 different points that are not differentiable, right? What are they? Do you remember? There are 4 points that are not differentiable on a graph. What are they? Those are points of discontinuity. There's 4 types of discontinuity, and those would be oscillating, a jump discontinuity, a replaceable. Okay, when we talk about where the graph is not differentiable, a cusp is one of them, a corner is another one. There's 2 more. A vertical tangent, and any place that's not continuous. You can't have a slope if there's not a graph. So those would be the different points on a graph that would not be differentiable, where it's discontinuous, where the graph has a corner or a cusp or a vertical tangent. So we have this, here we have, so my question again is this green graph here, the inverse of sine of x, is it differentiable for its entire domain? No. It's only differentiable for what? So it is different. So the inverse of tangent, this graph is differentiable for, let's do from -1 to 1, not including -1 and not including 1. Riley,
Yes.
I just walked in. Mr. Hall, don't ask me any questions because I don't know. I just walked in.
No, I'm
R-
getting it so far.
Riley, why is the green graph right here? Why is the green graph not differentiable at its endpoints?
Because it is not equal to those points, there's oh gosh, there's no point there.
There is a point there
There is?
Uh-huh.
Okay. Is it because it's a vertical tangent?
because we have a vertical tangent. Yep.
Okay.
The graph is not differentiable at a vertical tangent. Do you remember the other points? So there's 4 different points on a graph that are not differentiable. One is a vertical tangent. What's another one?
Cusp, and then any, I forget what it's called, but it's any point where we have, let's see,
Discontinuity.
discontinuity.
Okay.
That's it. And then fourth one would be,
Similar to a cusp. It's similar to a cusp.
oh yeah, that's right. Forgetting the name of it.
It's a corner.
Oh, corner, really?
Yep.
Yeah, that's right.
Corner, cusp, a vertical tangent, and any point that's discontinuous.
Okay, yeah.
Those are where the graph cannot be differentiable.
Okay.
And so these endpoints here turn into vertical tangents here and here, so they are not differentiable.
Right.
Okay, so I want to talk about, this is going to, whether you like it or not, this is the proof for the derivative. We are going to be adding 6 more cards to our flashcards today. And so we already know what the derivative of sine of x. What is the derivative of sine of x? It's cosine of x. So now we have to figure out what the derivative of the inverse of sine of x is. And so what I'm going to do, so let's look at y equals sine of x. When we find the inverse of a function algebraically, what do? What are the steps? There are 2 steps. Do you remember what they are? If I want to find the inverse algebraically, what are my steps? I switch the x and the y values. So that y now becomes the x and the x now becomes the y. What's the second step? After we switch the variables, we solve for y. Well, let's not worry about solving for y right now. That just takes us back to here, and then understanding how to find the derivative of this is going to be complicated. So I would like to use what we do know already to show what the inverse or the derivative of this inverse is. Now, if we take the derivative of this as it is, isn't this implicit differentiation? Do you remember how to do implicit differentiation? What is the derivative of the left-hand side? Yeah, this is just going to give me 1. And then the derivative of the right-hand side? Yeah, because this is going to be cosine of y. And then? We just took the derivative of the outside function? Yeah, times y prime. Yep, the derivative of the outside function times the derivative of the inside function. Now I want to, so that was implicit. Now let's go ahead and solve for y prime. So if I want to solve for y prime, what do I get? I get y prime equals what? Yeah, that gives us 1 over cosine of y. That's what we would have. Now I could stop of y. Yeah. I could stop there, but we're going to, I want to solve in terms of x. I want to solve in terms of x. So I take my x value, just like all of our other functions, I take my x value, plug it into here, and it'll tell me what my slope is for that x value on my graph. So what I'm going to do is I want to substitute something in for here, and I'm going to use the Pythagorean identity. Do you remember what the Pythagorean identity is? This is cosine squared of x, but I'm going to be using y, plus sine squared, yep, sine squared of y equals 1. Now I want to solve for cosine of y so I can substitute that in here. Now, ultimately, my goal is I really want to solve for x so that this, for any x value, I can just plug it into here and it'll tell me what my slope is for that x value. So I want to, is there any way I can solve for this in a way that I can take some, then I know what my cosine of y is and I can plug that into here. Okay, subtract sine squared of y, all right, so that gives us cosine squared y equals 1 minus sine squared y, and then we take the square root, because this is really the same thing as all of this squared. And so I'm going to take the square root of both sides. That gives me cosine. Cosine now is by itself. I'll continue to use red, I think, over here. So I have cosine of y equals the square root of 1 minus sine squared of y. Now you could do plus and minus there, but remember that we're just looking, in this case, we're just looking, when we were looking at our original function, that was for values in what quadrants? I'm sorry, for the inverse. The inverse of sine of y is in what quadrants? Only the first and the fourth. Where your cosine is what? Cosine is your x. Cosine is positive. So we're not going to remember plus, or we don't need to do that because we're only looking at where the quadrants where cosine or x value is positive. So I'm going to substitute that in. I'm going to actually just erase all of this here. I'm going to just substitute that in. So I have y prime equals 1 over the square root of 1 minus sine squared of y. That's a lot of work for nothing, because my goal was to rewrite this in terms of x, so that I would know for any value of x, I would know what our slope is for any value of x. But I don't have an x, I still have a y. Thoughts? Nobody has any thoughts? Starts with an S.
So if x is equal to the sine of y.
Yeah, let's substitute. Let's substitute. If sine of y equals x, that's substituted into here so that our equation will solve for any value. It'll tell us what our slope is for any value of x. So we're going to take that and plug it in. So sine of y, so doesn't that become x squared? Doesn't that become x squared?
Yes.
Okay, that becomes x squared. So that becomes a card. That becomes our card. Y prime equals 1 over the square root of 1 minus x squared. Now the co-functions are always easier. Or if you have all of the functions memorized, the co-functions are easier. Well, what the heck is a co-function? Well, sine of x, its co-function is cosine. Any idea what the co-function of tangent is? Cotangent. Any idea what the co-function of secant is? Cosecant. what happened before when we were talking about that, what happened when I have, let's go ahead and look at our flashcards again. Consider the co-functions. Oops, that's not, I didn't. Okay, I'm going to open this. Is this a co-function? No, because it's just secant. It's not cosecant, it's just secant. And it's positive. Look at this one. Is this a co-function? Yeah, it's cosine. So it's negative. Let's look at the next one. Is this a co-function? So it is negative. Is this a co-function? Yes, it's cosecant. So it is negative. This one here is that a co-function? No, so it's positive. Is this a co-function? No, so it's positive. So let's consider any guesses after all of that talk. So sine, the inverse of sine, so our card is, one side we have this, and the other side we have y equals sine of x, the inverse of sine of x. And so the derivative of the inverse of sine of x is positive. It's something we have to memorize. Any guesses what, if we have the inverse of cosine of x, what that would be? I'm missing something. Yeah, just make it negative. These are actually easier. If you have the first one memorized, then the co-function is just negative. Now we could go through the proof. We could go through the same proof to show that that is the case, but we don't have to. Okay, continue. Let's do another one. What's that? What if I zoom out? Is that too small? Is that too small? I can zoom in if you'd prefer. How many more cards do we have to do? Yeah, we're going to do a total of 6 cards today, and we just did 2. So we have 4 more cards. Now I'm not going to do all of the proofs. If you want to do the proofs, you're welcome to. In fact, it would be maybe a fun discovery if you have time to do that. But ultimately, I am concerned about time, and so I'm going to just skip the other proofs. And if I give you, Fernanda, were you done with this, or am I going too fast? You're good, okay. So the next card, if I have y equals the inverse of tangent of x, then the card, or then the other side of the card, is going to be 1 over x squared plus 1. You're going to have to use, if you wanted to do a proof of this, you're going to have to use that, the quotient rule, right? The quotient identity of sine of x over x, and do the same method that we did before. All right, any guesses if I need to find the inverse or the derivative of the inverse of cotangent? Yeah, because it's a co-function. So it becomes negative 1 over x squared plus 1. And there you go. Now, the next two are a little bit more complicated. So I said we're doing 6 cards. We have just finished 4. So there's 2 more. If I have the inverse of secant of x, and I'm trying to find the derivative of the inverse of secant of x, then that becomes, this is the more complicated one, where I have 1 over the absolute value of x times the square root of x squared minus 1. Any guesses what the derivative of the inverse of cosecant is? Yeah, it's a co-function. So we're going to make it negative 1 over the absolute value of x times the square root of x squared minus 1. I agree that these are not pretty. In fact, they're a little bit scary. But it's just a matter of getting used to it and adding these to our flashcards and seeing them regularly before we start to have them memorized. How you doing, Andrew? Is everybody caught up? Kyle, you caught up? Now, we're going to be learning, I always think it's interesting thinking of a calculus class being the majority of a calculus class is teaching the shortcuts. Because where do all these come from to start with, to begin with? It really has to do with, that idea of limits. Limits as h approaches 0. So what's the bigger picture? What does the derivative do? What's the point of calculating a derivative? Yeah, it gives you the instantaneous rate of change for any value of x. It tells you that instantaneous rate of change for any value of x. All right, so let's go ahead and I'm going to close this out for now. I'm going to open up this other one. This other file on flashcards. Okay, what is the derivative of secant of x? Secant of x times tangent of x. Yep. What is the derivative of cosine of x? Negative sine of x. Good. What's the limit as x approaches infinity of sine of x over x? 0. What is the derivative of cotangent of x? Negative cosecant squared of x. Good. What is the derivative of cosecant of x? Is it positive or negative? Because it's a cofunction. What is it? Yeah, it's negative cosecant of x times cotangent of x. Nice. Okay. What is the limit as x approaches infinity of cosine of x over x? 0. What's the limit as x approaches 0 of sine of x over x? 1. What is the derivative of sine of x? Cosine of x. What is the derivative of tangent of x? negative, oh, sorry, positive, because it's not a cofunction, right? It's just secant squared of x. Nice. Oh, here we get into some complicated ones because these are inverses. We have to know all 6 of these. What is the derivative of the inverse of sine? Nice. What is the derivative of the inverse of cosine? Nice. What is the derivative of the inverse of tangent of x? Nice. What is the derivative of the inverse of cotangent of x? I think I lost you guys. Let's start over. Let's go back and ask again. What is the derivative of the inverse of cotangent of x? Nice. What is the derivative of the inverse of secant of x? What did we finish that? I don't know if we finished that. One more time. 1. Nice. What is the derivative of the inverse of secant, cosecant of x? Nice. These, we have to memorize all these. And we're not done with the flashcards. We're going to continue adding to the flashcards as we continue. I actually don't think there's a lot more. To me, it seems like we have 4 more. I think we have 4 more flashcards, and then we'll be done with the bulk of the flashcards. Now, when we start talking about the integral, which is the inverse of a tangent, then we're going to have to remember to go backward. I'm going to have to show you these cards, and you're going to have to say what the function, if this is the derivative, then what was the function, right? Isn't that what we'd have to do with an inverse? Isn't that what we'd have to do with an inverse? Yeah. If I give you if I say what is the derivative of the inverse of cosecant of x, then we need to have it memorized that the derivative is negative 1 over the absolute value of x times the square root of x squared minus 1. But when we start talking about the integral, which is the inverse of a derivative, then we need to know what this becomes going backward. If I take the integral of this, then what do I get? We're going backward. And in this case, using the integral of this would give me the inverse of cosecant of x.
What's the notation of that? How would we see that on a problem? Would it just be y prime and then -1?
So the question is, so here's the really cool relationship. This is so cool. Let's look at, this is sort of a holistic idea. Right now, we're not talking specifically about today's instruction. I'm talking about all of the instruction on calculus. The idea of calculus, it all comes to this idea of finding the instantaneous rate of change. Now, let's say that we have some graph here and we have some curve here like this, and this is time versus distance, and I want to find the instantaneous rate of change at some point. Then describe to me, Riley, what it means. What would the units be? What am I talking about when I ask for the instantaneous rate of change? That becomes what? What are my units? Or what's the concept we're talking about?
For this graph in particular, it's distance over time.
Distance over time, which is what?
Velocity.
Distance over time, which is velocity. So when we have a distance versus time graph and we're trying to find the slope, the instantaneous rate of change somewhere, then the slope equals our velocity. Now let's go backward. Let's look at a graph that's not distance versus time, but one that is velocity versus time. This is time, and this is velocity. I don't know, let's say that this is, I don't know, 40 miles per hour right there over 1, 2, 3, 4, 5 hours. If I'm going, let's just keep it simple. If I keep a steady velocity for 5 hours, how far did I travel? The question is distance, not velocity. If I travel 40 miles per hour for 5 hours, how far did I travel? Now we're going backward to distance. How did you get 200 miles? That is a crazy idea. It took Isaac Newton a while to wrap his head around that. The inverse of an instantaneous rate of change is area? What? That's sort of a cool idea. And because of that, if I wanted to find, for example, I have, so if I have y equals x squared plus 3x, and I want to find the derivative of this, the derivative is what? Let me add one more thing, plus 7. Okay, so the derivative of this would be what? One more time. 2x plus 3. Now, Riley, your original question was about notation.
Yeah.
So I'm about to show you the notation, but we're not there yet. We're going to be talking about this probably after Christmas, right? It'll be a while. So, but Riley asked about the notation for the inverse of a derivative. And the notation looks like an S that's been, I don't know, vertically stretched. So if I want to find the derivative, the integral of 2x plus 3, and I'm going to say with respect to x, so I have to write this other piece here that probably is going to bother you over time. I don't know. Actually, over time, I think you'll get used to it. So what this means is the integral of this function with respect to x. That's how I write it. You were asking about notation, and I'm showing it to you right now. The answer to that is what? X squared plus 3x plus, we don't know how to get, if I don't see this, I don't know how to get back to that. I don't know where I don't know what happened to it. I just dropped it, right? To go from here to here, I dropped it because the derivative of a constant is 0. So this disappears. So it can be anything. And so to being able to go backward without seeing this, I don't know what that is.
Do we have to solve?
No, we will say plus C because we don't know what it is. Unless, well, I know what it is at 7, but if I didn't know what it was, then I wouldn't be able to go. I wouldn't be able to rediscover the 7.
In a real world application, though, wouldn't it be crucial to know that? So how would you use the integral in this case?
So a lot of times we use what's called the fundamental theorem of calculus, and we're going to evaluate. We'll talk about this later, but when you're trying to figure out the real world application, like you're trying to figure out the distance traveled, if you're trying to find the distance traveled, usually there's another piece of information you need to know to be able to bring back the 7. Usually when I laughed or whatever else, there's some other information that we need in order to bring that back. When we're trying to figure out the distance traveled, then you were talking about that shaded area, right? Yeah. Then the displacement. The displacement will give me this. Right. I just throw that in, it tells me what my displacement is. But so if I start up here And then at, I don't know, isn't that my y-intercept? So if I had something like, what does that become? I don't know, something like some graph like this. So if I'm trying to figure out this area here using that graph, I'm going to say, I'm going to give myself limits of integration. I'm getting way off the top. I better stop. I better stop talking about this because we're getting off topic and we need to focus on today's topic. And I think there's always going to be a, but what if, but what about this? What about this? And then we've lost all of class time. So you wanted to know about the notation. There you go. We need to get back on track. Okay. And besides, I do think if we don't really learn all the other stuff about derivatives, then talking about integrals can be confusing. So I'm going to go backward. I'm going to zoom out. So I think I just think this is fascinating. It's absolutely fascinating, this idea of finding the instantaneous rate of change. The inverse of that is the area under the curve. Huh, crazy. Crazy. Okay, so let's go ahead and talk about, let's do some examples. Okay, I do want to talk about the notation. If I'm going too fast, let me know. I want to talk about the notation for the derivative of the inverse. The derivative, the notation for the derivative of an inverse is f, or the inverse of f of x prime of x. We can also write it this way. This is less common, but it is still possible to see it written like this. That's less common. It's this, you're going to see it more like this. Let's do an example. Okay, are you good? Okay, scroll to the top. Here's our example. If x of t equals the inverse of sine of 1 minus t, then x prime of t equals what? Incidentally, what would this mean in terms of physics? That's our position. That's our position. So if we took the derivative of that, that's going to give us our velocity. Kyla, did you figure it out?
No, I didn't get a chance to write down the flashcards, so I'm looking at
Oh, okay. Miguel? I think that would be awesome. Yes, sir.
So since we got the inverse of sin, wouldn't we just plug in the y prime equals 1 over square root of 1, subtract it.
Okay, one more time. 1 over what?
1 over the square root of 1 minus x squared.
Is that it?
We would have to replace the x in that with 1 minus t.
Nice. 1 minus t squared, okay. No, doesn't this look suspiciously like the chain rule to me? Because don't we have a function inside of another function? So what you just did, Miguel, is you just took the derivative of the outside function. To solve using the chain rule, what's the next step? So it's times the derivative of the inside function. What is the derivative of the inside function? It's -1. This piece here, the derivative of a constant is 0. The derivative of negative t is negative. So don't we have to, using the power rule, where we have a times x to the power of n, we multiply our a, our coefficient, by our exponent, and then we subtract 1 from our exponent. So what we have then is with -1 is we have, negative t is -1t to the power of 1, right? So using the power rule, that would give me -1 times 1 times t to the power of what is anything to the power of 0? Yeah, it's 1. So I have -1 times 1 times 1, which is what? Yeah, so this is -1. So the derivative of the inside was -1. Now I would stop here. If this is free response, then stop here and you're good. Because they're not trying to, AP or College Board is not trying to measure your ability to do arithmetic. They are measuring your understanding of calculus. Now, the only problem I can think of is, what if this is multiple choice? My guess is that this is not going to be one of the choices, which means I'm going to have to simplify. So if this was multiple choice and I have to simplify, any suggestions on how I could do that? Is there a way I can simplify this besides just making this negative up here because of this negative? Do what?
That's squared, so we can, we already know the square root of it. So, would we do, would it be 1 minus t times the square root of 1?
1 minus t and times the square root of 1?
Yeah.
What happened? Let's expand this. Let's try to expand this and then just do some arithmetic. So I have t x prime of t equals 1 over the square root of 1 minus, and then in parentheses, if I have 1 minus t squared, isn't that the same as 1 minus t times 1 minus t? Oops. Minus t, does that look right to you? Besides being messy. So now what? What's that called? Louder? Is that a difference of squares? No, it's not a difference of squares. I just expanded it. So what, so I'm going to do what? Starts with a D. I'm going to distribute. So that gives me x prime of t equals 1 over the square root of 1 minus, and all in parentheses, I'm going to distribute. I have 1 minus t plus t squared. Agreed or not?
Yes.
Okay. And then I can clean this up a little bit. So I have 1 over the square root of 1 minus, in parentheses, 1 minus 2t plus t squared. Now what? Any suggestions? Nice. Yep. Let's distribute the -1. So that gives us the square root of 1 minus 1 plus 2t minus t squared. Louder. Okay, if I combine like terms, those ones disappear, don't they? I have 1 minus 1, which is 0. So I have 1 over the square root of 2t minus t squared. I don't think we can do much better than that. Although I forgot something important. There's something I lost along the way. Yeah, what happened to my negative? What happened to that negative? I lost that negative along the way. This should have been, oops, did I lose? Okay. Yeah, that negative should have been here all the way along. Which is correct? The negative here, the negative here, or the negative here?
All are correct.
Yep, they're all correct. I don't care which one, whichever you feel comfortable with. They're all the same. A negative here, a negative here, or a negative here. It's all the same. Kyla, what do you think? Aren't you Kyla? Oh, what do you think, Kyla? Okay. Yeah, it really, if you're confused at all, it really comes down to, we just need to memorize these. We just need to memorize. Just memorize these. These are our shortcuts. All of our rules. The class that teaches shortcuts. Okay, here's another one. This should not be confused with this. What does this mean? Yeah, this is the derivative. What does this mean? Find the derivative. Think time? Andrew, did you get it?
I did not.
Do you remember what the derivative of the inverse of cosine is?
It's -1/x squared.
Okay, so does that mean that the answer is -1 over the square root of 1 minus x squared? How is it different? What am I missing? I'm missing what? I'm sorry.
Missing one.
Isn't this the chain rule?
Oh. Yeah.
So how do I need to change this?
Make it like the, what's it called?
It wasn't really x, right? So that x needs, remember we take the derivative of the outside function times the derivative of the inside function? Andrew?
Yeah.
So what goes here instead of the x? Yeah. So that's taking the derivative of the outside function times. Sometimes helps to rewrite this. Using our law of exponents, what is 1 over x the same as? X to the power -1. Okay. So if we take the derivative of that, what do we get?
Negative x to the square root, sorry, x to the negative second.
Yep. Yep. And if you want to stop right there, if this was free response, you should stop right there. I'm guessing though that the answer that's going to be given to us as multiple choice would be this one here. So negative times the negative is a positive. This is a negative x1, and I'll move it to the denominator to get 1 over x squared times the square root of 1 minus 1 over x all squared, something like that. That's probably going to be your multiple choice option. Okay, moving on unless you have a question. Fernanda, how are you doing? Go. I want to find an equation for the line tangent to the graph of f of x equals the inverse of tangent of x at x equals 1. Kyle, if we're going to find a tangent line, what equation do we need to think of? What's our generic equation we need to consider? Y equals M X plus B, because it's a line. What am I missing? What do I need? I need my X and my B, right? Once I have an X and a B, that gives you all of your infinite solutions. That would make our line. So how do I do it? How do I find M? Yep, so M is the derivative of f of at 1, right? 1 equals what is the derivative of the inverse of tangent of x?
Ultimately, you get 1/2, but
It's 1 over x squared plus 1, right? But x is what? It's 1, so I have 1 over 1 squared plus 1, which gives us 1 over 1 plus 1, which is 1 over 2.
yes.
Okay. So we have our M value. How do I find the B value? I have the M value. How do I find the B value? Well, if we start plugging things in, what do I have? I have y equals 1/2 x is 1 plus b. Do I have enough information to find b? What do I need to find b? I need a y value. How do I find a y value? Yeah, take the x, plug it into the original. It tells me what my y value is. So so I have y equals the inverse of tangent of 1. I'll consider what that means. Because it's an inverse, we have tangent of some angle equals 1. Isn't that what that means? What is an angle that gives us a tangent of some angle that gives us 1? What is it? Pi fourths, yeah, pi fourths. Remember our hand trick? Remember that tangent of x is equal, with using our quotient identity, is equal to sine of x over cosine of x. So what is an angle? If sine of x over cosine of x equals 1, then what finger do I put down so that sine of x and cosine of x are the same so that I get 1? And the only answer is the middle finger. Remember, from our sine direction, we have the square root of 2 over 2. From our cosine direction, we have the square root of 2 over 2. So we have the square root of 2 over 2 over the square root of 2 over 2 gives us 1 if theta is pi fourths. So our y is pi fourths. So y equals pi fourths. Okay, so now we know what our y is. So I have pi fourths equals 1/2 plus b. Now what? How do we solve for b? Right, subtract 1/2 from both sides. So I have pi fourths minus, and what's the rule when we add fractions or subtract fractions? Yeah, and so 1/2 is the same thing as 2/4 equals b. So b equals what? Pi minus 2/4. Does that look right to you? So the tangent line is what? Y equals what? 1/2 x plus pi minus 2/4. Let's see if it works. Let's see if it works. I'm going to go to Desmos. Open up that one. Okay, so our original equation was so I have f of x equals the inverse of tangent of x, and we get this graph like this. And I want to know at the point of 1 comma pi fourths. Oops, what happened there? 1 comma pi fourths at this point right here, what the equation of that tangent line is. Well, we calculated it to be here at y equals 1/2 x plus, in parentheses, pi minus 2 divided by 4. How did we do? How do you guys feel we did? Pretty good? Okay. Yep. Did you finish copying? Okay. Scrolling down then. Here's the general rule for inverses. For the coordinates of A comma B with inverse. What's the inverse of, if I have a point of AB on a function, what would the inverse point be? Yeah, it would be B comma A. If f prime of A equals m, that's my slope, when x is A, then the inverse of f prime of B equals 1/m. You just get the reciprocal. So let's do an example so that this will make more sense. Usually makes more sense when we have an example. So I have f of x equals x to the power of 5 plus 2x to the power of 3 plus x minus 1. The derivative of this is what?
Or 5x plus 6x squared plus actually
Plus 1?
plus 1 minus 1.
Plus 1 plus 0?
Actually, no, that's 0. So yeah.
Plus 1 plus 0. Yep. Okay, I want to know what f of 1 is. What am I asking when I ask for f of 1? What equation do I use? The first one or the second one? Yeah, I'm going to use the first one. And what do I get? I get, if I plug in 1 here, oops, wrong tool. Yeah, it's 3. I get 1 plus 2 plus 1 minus 1 equals 3. So, so the inverse, I'll go back to blue. So the inverse, gosh, okay, all these weird. So the inverse of f of x of f of, the inverse of f of 3 is what? We should be able to tell from this piece here what the inverse of 3 is, the inverse of f of 3. Consider these points. Consider these points. What happens to your x and y's? They switch. So if I have f of 1 equals 3, then what's the inverse of 3? Louder? It's 1. Okay. Now if I find the derivative of this, f prime of 1, that's the slope. What is the slope when x is 1? Do I use our first equation or our second equation? Second equation. So when I plug in 1, what do I get? 5 plus 6 plus 1, which is what? It's 12. What is the derivative of the inverse of f of 3? Thoughts? Yeah, it's 1 over 12. The answer is 1 over 12. Oh, what happened to my 12? 1 over 12. There we go.